these event-based sensors are both sparse and fast at the same time. And this is totally breaking a limitation of conventional imaging sensors.
And each pixel is activated independently from the other. And that leads to an incredible dynamic range, significantly higher than a conventional frame-based sensor, because you don't have this concept of exposure time.
Welcome to a new episode of our Envision podcast, 5 Questions 2. Our topics are image processing, machine and embedded vision, AI and metrology. My name is Peter Ebert, Editor-in-Chief of Envision, and I'm happy to have you here for a new episode. This episode is all about the latest innovations from IDS, the first event-based vision camera. We took the opportunity to speak with experts from IDS and Prophesee, the manufacturer of the event-based sensors. Together we dive deep into the technology, explore exciting application areas, and take a look into the future to find out what exciting developments await us in the field of event-based vision. So, hello everyone. We have 2 guests. First is Boris Duché, Product Business Manager at IDS Imaging Development Systems, and Christoph Posch, CTO at Prophesee. First question is, of course, what is event-based vision and what are the advantages compared to image-based vision systems? Maybe, Christoph, you would like to start?
Hello, everyone. Let me start here from the fundamental difference maybe between conventional image-based vision systems and event-based vision. The fundamental difference is actually that a conventional imaging sensor, every pixel in the array of this sensor is asked 30 times a second or so, 60 times a second, what do you see? And all the pixels will respond to this question and send their measurement results out of the sensor. This happens over and over again. So every time this command is sent to the sensor will send back what we see as an image. Of course, this is a static snapshot in time of the visual scene that is in front of the sensor. Event-based vision works totally differently. So the pixels are not asked like again and again what they see, but they react themselves to what they see in the scene. So they react to changes and to motion in the scene. And if there's nothing happening in the field of view of the individual pixel, these pixels do not respond. It's very important to understand the pixels are independent and work autonomously and react to what's happening in the scene. The implications of this different approach to acquiring visual information, especially dynamic visual information, so information that changes, information about objects moving, etc., is as I said before, the pixels that are not seeing anything changing in the field of view just do not produce any data, do not produce any output. So, for example, non-changing parts of the scene, like a background that doesn't change, these pixels will not create any data. As a result, the data output of an event vision sensor is very sparse. So only pieces of the scene that convey information about the dynamics in the scene, only these data are put out of the sensor. Secondly, this can happen very fast. Pixels can react very, very quickly to these changes in their field of view. So these event-based sensors are both sparse and fast at the same time. And this is totally breaking a limitation of conventional imaging sensors. If you want higher temporal precision in your data, you have to increase the frame rate, you produce more and more data. And in event-based sensors, this limitation is totally removed. You can be fast and sparse at the same time. That means you have a very, very efficient way of acquiring this dynamic visual information. And you have a very, very high temporal precision in the data that allows a lot of applications. And we will come to that later in this talk, I think. So this is the main difference between these 2 approaches to acquire visual data.
Boris?
Yeah, Christoph, I have something to react on. I think also because the amount of data we acquire with an event-based sensor in comparison with a frame-based sensor, because the amount of data is much lower, the power consumption of the sensor is also lower than a conventional sensor. Am I right?
That is correct. Yes. One of the big claims of event-based vision, which is coming out of the field of neuromorphic technology, is indeed highest efficiency that translates into lowest power. Indeed, you get the saving in power consumption already at the sensor level, but even more when you think of a vision system, because you have to transmit the data to a compute element, to a processor, and then process this data there to extract the information that you need for your vision task. You also save a lot of power also in the transmission and the processing of the data. Yes, indeed, event-based vision excels in power consumption. It excels in the efficiency of the acquisition of the dynamic visual data and in the processing and up to the final result of the vision task. So yes, power consumption is indeed one of the greatest promises of event-based vision.
To make it clear, the big difference between classical machine vision is the end of frames per second. There are no frames per second anymore.
No frames, indeed. Yeah.
No frames at all, yeah.
Indeed, we have a time continuous stream of pixel individual data that come out of an event-based vision sensor. And the temporal precision of this data, as I said before, is extremely high. So these pixels can react to changes in the scene at time scales of the order of tens of microseconds, right? So you get information of the dynamics in the scene that you would get from a conventional imaging sensor if you would run it at tens of thousands of frames or even 100,000 frames per second. You can imagine how inefficient that would be if you image a scene that has large parts of an unchanging background, etc., this kind of things, where you would acquire the same information over and over and over again. All this data would be totally useless, wouldn't give you any new information that you need for your vision task, etc. So this approach to acquiring data is extremely efficient and completely removes all the redundancy that hampers the function and the operation of conventional imaging systems.
And how exactly does event-based vision capture image data in real time?
Exactly. So that all that happens at the pixel level, actually, as I started explaining before, in an event sensor, every individual pixel is autonomous. It doesn't interact with its neighboring pixels. It doesn't get external timing information. It doesn't get, for example, a frame clock like in a conventional image sensor. It doesn't get an order to do a measurement or so. But it reacts autonomously and independently of all the other pixels to what happens in the scene, in the field of view in front of each of these individual pixels. What the pixels actually do is, you could see it as a kind of a level crossing sampling operation. So if the light that the pixel sees, the light that falls onto the photodiode of each of these individual pixels changes by a certain relative amount, the pixels will react to this change by sending out a flag, a signal to the periphery that it saw a change, an event. All the pixels do this simultaneously, so all the pixels simply react to what happens in the scene in front of them and send out the requests of being acknowledged that they saw a change, that they created an event. And this the readout periphery then takes care of all these requests of the pixels and forms this time continuous stream of event data that is then streamed out of the event sensor. So every pixel is a little, if you want, a little asynchronous delta modulator or a level crossing sampler that samples the change in photo flux that receives at each of the pixels. And all the pixels do this independently of each other at the same time.
Thanks, Christoph. Boris, do you have something?
Yeah, I would have. I would say a little bit something about exposure time. On a conventional frame-based sensor, you have a parameter that is applied at the sensor level, which is called the exposure time, and it means each pixel of the frame-based sensor will be sensitive to light for a given period of time. And if you have a scene with very, very dark areas and very bright areas, you will have to find a trade-off in the exposure time you will use. You want the exposure time to be long enough for the dark side of the scene to be bright enough, but you don't want your exposure time to be too long because you would bloom all the information in the bright areas. And with event-based sensors, Christoph, correct me if I'm wrong, but you have no concept of exposure time. Either a pixel is activated, either it is not, and each pixel is activated independently from the other. And that leads to an incredible dynamic range when talking about event-based sensors, significantly higher than a conventional frame-based sensor, because you don't have this concept of exposure time. You have it's a little bit technical, but you have a logarithmic response curve at the sensor level, and that permits to achieve incredible dynamic range, meaning capacity for the sensor to acquire data in a scene that contains both very dark and very bright information.
Yeah, that's totally correct, Boris. Indeed, there is no exposure time in a pixel, in an event-based pixel. This and the fact that every pixel in the sensor array is independent of all the others, it is indeed possible that we get an extremely high intra-scene dynamic range. Intra-scene meaning that in the same scene at the same point in time, you can have extremely different light levels. For example, imagine a scene where a car drives into a tunnel, but it's still outside the tunnel, and the sun is in the field of view of the sensor, as well as the inside of the tunnel is in the field of view of the sensor. Because the event-based pixels are able to monitor their photocurrents for these changes, as explained before, over a very wide range of photocurrents, actually 6 to 7 orders of magnitude of photocurrents, from extremely dark to extremely bright. These pixels will actually do their job independently of all the others. So the pixels that look inside the tunnel don't even know that other pixels actually see the sun at the same time. All will do their relative change detection independently. By relative change, and this is also important because also as this results in this extremely high dynamic range, the event-based pixels react to relative changes and do not care about absolute light levels. So again, looking inside a tunnel or looking directly into the sun, for the pixels, doesn't matter. They only react to relative changes of a certain magnitude, which can be set by applying a threshold to these pixels, say 10%, 20% of threshold. So a change in light from, say, 1 lux to 1.1 lux would result in the generation of one event, as well as the change from 10,000 to 11,000 lux would also create one event in another pixel. So that indeed leads to this incredibly high dynamic range, which is another strong point for event-based vision, and is very, very helpful in many applications, like the one that I was just explaining, but there are many, many more. You can imagine that wide dynamic range is extremely useful in many applications.
Now we talked a lot about technology. Next question is, of course, which applications benefits most from the new technology? Maybe Boris, you will like to start now?
Yeah, I can start. So event-based sensors are really a disruptive technology, and it opens a huge variety of new applications we can solve in machine vision. Let me explain. Currently, the typical machine vision applications that you will find in the industry would be a frame-based sensors used on top of a conveyor belt, so that a single frame image is acquired every time a part is going underneath the camera. And then you will run some quality control algorithm to find a defect on the part. But basically, even though the conveyor belt is moving and you have, at a given frequency, you have a new part going underneath the camera, the algorithm is still running on a single frame image. Problem is when you want to track something with movement. Let's say you want to track an object that is moving on a scene. I'm thinking about sport analysis, for example, where you want to track the arms of a tennis player, you want to track something in the scene. Working with a frame-based sensors means working with a very high amount of data. Today, when you want with a conventional frame-based sensor to track an object moving in a video, either you have to record the video first, then process the video. That will take some time because it's a lot of data to process, and then you will analyze the results of the algorithm. The second option that you have would be to downscale the video, so to reduce artificially the resolution of the video so that you can process your tracking algorithm live. You find a lot of chipsets currently, especially in the CCTV industry, for example, for person detection, people detection, and people tracking that will run live on a frame-based system. But what they do, this kind of technology, they first downscale the image very significantly, typically to 256 to 256 pixels, and run the algorithm on this downscaled image. With event-based sensing, it opens really new doors for tracking moving objects, because the amount of data to process is significantly lower. You can run applications live where you process the data. So if you want to do sport analysis, you want to track an object moving on the scene, you want to track someone moving on the scene, it is a perfect technology. You can run it live. And obviously, it's not only about sport analysis, but also in the scientific fields, we have applications where we want to track particles moving at a very, very high speed that you can track live with event-based technology. And now I am talking about an object moving on the scene, but sometimes a huge part of the scene is moving. I'm thinking here, for example, about vibration monitoring. Today, if you want to track how much an engine is vibrating, whether it is in the car or an engine that is used in the factory, you cannot track these vibrations with a frame-based sensors, or at least you cannot run it live. With event-based sensors, we could solve some applications for predictive maintenance, where we track the variation of vibration of an engine, and anytime we see that the vibration is going away from the normal state, let's say the vibration is increasing typically, or the amplitude of the vibration is increasing, then we know that we have to do some maintenance. So it really opens a lot of new doors, new applications for machine vision applications. And obviously, I would also add a little something when it comes to 3D measurements. Today, 3D cameras are used very, very often in robot guidance applications, but you are limited in 3D systems, not by the quality of the data you can acquire, but by the speed of the data acquired, because it's a lot of data to transmit from the camera to the system, and then you have the 3D algorithms running on a lot of data. Event-based sensors opened a new door when it comes to 3D technology, and a lot of companies are working to integrate this technology on a 3D system. Christoph, something to add maybe?
Yeah, sure. So I totally agree what you say. All these applications that we're mentioning are absolutely on spot. And ideally, actually, really event-based vision excels in applications where things move, or ideally where things move fast. And even better is where things move and things move fast, and there's the lighting conditions are uncontrolled. This is where event-based vision really has advantages. If you then have constrained resources because you are running on a battery-powered system, or your camera is moving because it's on a drone or something, if you have restrictions in terms of data transmission bandwidth, or in terms of battery lifetime or so, these are the ideal applications for event-based vision, because event-based vision is fast, it's sparse, and it has this huge dynamic range that allows to operate under uncontrolled lighting conditions. So now you can imagine where all these applications are, where things move, basically. So it starts from drone navigation, robots, automotive, for example, of course, but also in industrial, as Boris just mentioned, industrial automation, industrial process monitoring, etc. You can monitor laser welding processes, for example, because of this huge dynamic range of the sensor. At the same time, it's very good in conveyor belt applications, etc. So everywhere where things move fast and you need to process this information in real time, perhaps take decisions in real time about, for example, in an automotive scenario where you want to activate your brakes in an emergency scenario, or in a drone navigation where you want to avoid an obstacle or so, you can use this event data from the sensor to do in a closed loop real-time processing and real-time operation of a system. This is extremely difficult for conventional imaging systems, because maybe the frame rate is too slow to follow the fast evolution of what's happening in the scene, or you cannot get the data fast enough out of the camera, or you cannot process this data quickly enough to be able to close a control loop in real time. All these things come together to solve vision applications that are very, very challenging for conventional imaging systems based on frame-based sensors.
We talked about technology, applications. Now I have a question about software. What about software integration or SDKs for event-based vision? What is available? Maybe Boris, you like to start?
Yeah, I can start in here. It's important to understand, as a camera manufacturer, usually we provide the SDK, so the software package to communicate with the camera so that you can acquire an image, a single frame image. And then you have plenty of libraries, open source libraries or proprietary libraries that you will find out there to process the frame, to process the image, and to run your own algorithms to solve your applications. Now, when you talk about event-based sensings, it's not a frame anymore that you get out of the camera. It is a continuous stream of events, and events are defined as a very, very basic data structure. Actually, you just have the pixel position, so that's the X, Y position of the pixels that is activated. You have a timestamp, and you have the polarity, which means the light intensity is going up or down. So it's a very, very basic information, very basic structure, but you get it at a very high frequency typically. Because of these different kind of outputs that you get out of the camera, you would not work with a conventional image processing library, like thinking about OpenCV, for example. You need different kind of libraries. And this is why we made the decision at IDS, following the strategy of Prophesee. Prophesee, in the very early stage of the company, they understood that they needed to provide not only the SDK to communicate with the sensor, but also the SDK to process the event stream. So we decided at IDS, bringing a camera based on this sensor, to work closely with Prophesee, and you operate the camera with the Prophesee MetaVision SDK that permits not only to get access to the event stream coming out of the camera, but also to process the event stream coming out of the camera. And then I would leave it to you, Christoph. Maybe you want to explain a little bit more what this is about.
Yeah, sure. So what you say again is very correct. At Prophesee, we started on the premise that you cannot just build event sensors and give them to a customer and good luck with your new sensor and go ahead and do what you want, because this type of data and the way information is encoded in this data is not very common yet. People working on images and frames since decades, and this way of encoding visual information is well understood, and many people know how to work with it. But not many people understand how to work with events. And that was clear to us from the beginning. So we started to develop in parallel to the sensors also the applications and the processing algorithms. And all this comes together in this MetaVision SDK, as Boris just mentioned, that contains not only the drivers and the firmware and the basic tools to operate the sensor, but also it contains code snippets, application examples, code examples for low-level vision tasks like tracking, optical flow, this kind of things. Also some higher level applications, also some first machine learning models because event-based data are also very well processed using machine learning techniques. And this is actually another point that we may want to discuss in this podcast. So yes, it is very important to support the user in the end in the development of the application, in the development of the machine vision algorithms or machine learning based algorithms that extract the information out of the events to solve the vision task at hand. This is very important, and indeed we take a lot of care to develop further this tool set, this what we call MetaVision SDK, that contains all these bricks that support the user to develop their own applications based on event-based sensors and event-based vision in general.
Thank you. So we're coming to our last question already. Where do you see limitations of event-based vision, and what are the future developments we can expect? Boris, you like to start again?
Yeah, I can start, and that would be a follow-up to what Christoph just said. So because the output of an event-based sensor is not an image, but an event stream, the first things we have to do, the first limitation I see, and I hope that we will overcome it also via this podcast, and thank you so much, Peter, we need to educate our customers, because our customers are typically machine vision specialists, image specialists, engineers that went to engineering school for image processing. And in the school, in the studies, they worked on frame-based images. They did not work on an event stream. So the first thing we have to do at the moment is to educate our customer base how you can work, how you can run an algorithm on an event stream. What is the difference with a conventional frame-based sensor? And then to follow up, one of the limitations so far of event-based technology was the price. The price of an event-based sensor is higher than the price of a conventional sensor, not because it is complex to make. It is basically the factory process to build the sensor is very similar to a conventional frame-based CMOS sensor. But because the volume of production is lower at the moment, because it's a very new technology, the price of the sensor is higher. We could make at IDS a camera for a reasonable price. Let's say it is still a higher price than the conventional frame-based camera, but it is acceptable. We get very, very good feedback from our customer base. We hope with the success of this camera, and we see a lot of interest in this technology, the volume of the event-based sensors will get higher and the price will diminish over time. And then to finish, today, the sensors that we integrate, the IMX 636, is limited in resolution to 1.2 megapixel. Once again, when you work with event-based sensor, your goal is not to have the most resolution, the most information as possible. You want to lower the amount of information that you get. So you are not running the race of higher resolution. Yet, if you want to find small details moving at a very high frequency on your scene, we expect to see higher resolution sensors in the future. And maybe, Christoph, you can say a little bit of something in here.
A few points have been raised here. First, about the price. Maybe indeed there is no fundamental reason why event-based sensors should be more expensive than conventional image sensors, because indeed they are fabricated using exact same fabrication technologies. This is as CMOS processes typically of image. They call CMOS image sensor processes that they are enhanced for this photon transduction, but they are in principle standard CMOS processes, and the same are used for event sensors as well as for conventional image sensors. So at the same volumes, with the same chip size and the same volume, the price of an event sensor and the frame sensor is the same. So indeed, it only is a matter of production volume that will be driving down the price of event vision sensors in the future. Secondly, the question about resolution, indeed, in the past, or from the beginning of times, actually, event sensors always had larger pixels than conventional imaging sensors. The reason is that in every event pixel, there's a large amount of circuitry. There are up to, let's say, 80 up to 100 transistors per pixel next to the photodiode and a few other components. Whereas in the conventional image sensor pixel, there is just a photodiode and 2 or 3, 4, maybe 5 transistors. That's all. So we have much, much more to put inside each of the pixels. By going to ever more advanced fabrication technologies, event-based vision has been able to catch up. The pixel sizes now, as we use, for example, stacking processes, is approaching this pixel sizes of conventional global shutter image sensors. As the first event sensors had pixel sizes of 30 by 30 micrometers, today we can build event pixels of the size of 3 by 3 micrometers, which is approaching the sizes of global shutter pixels. So this is a reduction in a factor of 100 smaller over the past years. That shows how the development of event vision sensors has actually accelerated in the past years. But when it comes to resolution, of course, smaller pixels help because you can build sensors with larger array sizes that have still a reasonable chip sizes. Indeed, our Generation 4 sensor has a 1 megapixel array resolution. And indeed, there may be applications in the future where you need even larger array sizes. For example, automotive, where you want to see further, etc., these kind of things. So we indeed expect array sizes in the future of maybe 2, maybe 4 megapixels for the upcoming generations of event sensors. On the other hand, however, it is possible to a certain extent trade off this extremely high temporal resolution with spatial resolution. Actually, our last sensor generation has very, very small array sizes. Our last sensor generation, we call GenX 320, has only 320 by 320 pixels, a very, very small sensor, a bit bigger than a millimeter aside of the chip. So really, really very small for applications in IoT, XR, AR, VR, and similar applications. Appliances, etc. So here you don't need high spatial resolution, but you still benefit from the high temporal resolution, say for eye tracking, for example, in XR devices. So here we go actually the opposite. We go to smaller array sizes and smaller chips. Also, of course, here again, power consumption is important. This newest generation of sensors consume less than 1 milliwatt in operation. So hundreds of microwatts is enough to drive this sensor in this high temporal precision operation, which is an order or two of magnitudes of lower power consumption than conventional sensors would have in similar settings. So yeah, indeed, these two directions, higher resolution, yes, it will come as well. But also there's this trend towards very, very small, very power efficient, also small area size event sensors. And another thing that I see coming in the future for event-based vision is the processing part, which will become even more interesting and more important because the efficient processing of event data, as they are not frames, as we saw before, there exist a lot of know-how, a lot of techniques to process this data in an efficient way. It is very important to also treat event data and process event data in an efficient way, which is not possible using conventional computational architectures like CPUs or GPUs, which are typically used, for example, for machine learning-based image processing. So indeed, we need to go to different compute architectures. And here we are talking about developments in AI in the direction of spiky neural networks and graph neural networks. And this will be the future for processing event data in an even more efficient way. So we will then benefit not only from the efficiency in the sensing, but also in the efficiency of processing and get to a completely new level of vision, efficiency, power consumption, etc., that will excel even more and bring event-based vision to a new level where it then will hopefully be able to be employed in mass market applications, consumer applications, etc., and this will then be the breakthrough for event-based vision, I believe.
It's a very complex technology. It's a very, very innovative technology. So I'm quite happy that we had the chance to have you here as our guests, Boris and Christoph. I would like to say a big thank you, and hopefully we'll hear a lot of things about event-based vision cameras in the near future.
Thank you so much, Peter.
Thank you, Peter. It was great.
Bye.
Bye-bye.
If you would like to find out more about InVision, please register for our InVision newsletter at invision-news.de/news, become a follower of our LinkedIn channel InVision News, or find out about our webinars at invision-news.com/Tech Talks. I look forward to welcoming you to our next episode of our InVision podcast, 5 Questions 2.